So what we're saying is they have the same number. Why do they have the same number? U205, 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 because they're inside the same package, right? But what I'm saying is this guy is saying if this was drawn as an OR, I would be confused. For number one, if that was drawn as a NOR, I would have a low active output feeding a high active input, which right off the bat tells you something's wrong. Here I have a high active output feeding a what? A high active input. So that's the kind of stuff you're looking for. But this gate is not looking for any high to get a low. This circuit right here is looking for all lows to get a what? To get a high. This gate's looking for all lows to get a high. They didn't need to use this input, so they tied it active, right? You understand? Yes or no? Because that's the symbol for what? Common, yeah. They didn't need this input, so they tied it to common. And we'll look at that, how to time. Now this is an OR gate. If I looked up a 74 LS32, it would show me an OR gate. So when you go to the data sheets, all your data sheets are drawn in positive logic. Then when we get into the circuit, hopefully the people who drew it in active logic. So this is telling me this guy's looking for what? All lows to get a low. Now, if it was drawn as an OR gate, I would have a high active output feeding a low active input, right? And something, I know something's wrong. So you can't have a low active, if it's drawn in active logic, you can't have a low active output feeding a high active input, right? Does that make sense or vice versa? So this is what I call active logic. Active logic is the gates are drawn using either the positive logic symbol or the negative logic symbol, showing you what the gate is actually looking for to make this circuit work. A low can feed a low, and a high can feed a high. But it don't mean it's wrong. It just means that would catch my eye, right? You understand? It doesn't mean it's wrong. It just means it might be serving that function in logic. But normally we don't have in active logic. Normally we don't have a low active input feeding a high active output. I mean, a low active output feeding a high active input, or a high active output feeding a low active. That's not normal. It don't mean you won't ever run into it. We're going to look at some truth tables, and some of the truth tables talks about the inputs being invalid. And I learned a long time ago, if any input combination is available to an engineer, some engineer somewhere is going to use that. They're not going to use it as invalid. They're going to use it to do something, right? You understand? So be careful about inputs that are labeled invalid in the truth tables. Huh? Well, no, you're looking at the output relative to the input. We're saying this low active output should feed wherever this guy right here goes. Wherever it goes should be a low active input. So if I follow this and I follow this and I follow this and I follow this and I go over here, it's not a low active input. It's an input that changes the directions what it is. So high would be one direction and low would be other direction. So this guy is, you understand what I'm saying? It's not invalid because the output is high active and the inputs are low active. What I'm looking for is I'm looking for this low active input to be fed by a what? Low active output of the previous gate. Understand, Michael? So we're not saying what's going on here. We're saying what? So this guy says this guy right here says it's what? A high active input. So what's it looking for? It's looking for a high active output. That makes sense now. So it's not what's going on with the gate. It's relative to the inputs and outputs. Now, if I go over to FD, so let's find floppy disk. So I think it's RAM. So you're actually looking at, I'm looking at floppy disk. Oh my goodness, I don't have the right one. I'm looking at FDC 1. I wish I had it in mind because I can't see it when it's in this thing right here. So this is on the left-hand side, coming in. Now what I see here is I see a low active output feeding a watt. So I'm confused. Because that means this guy, if you look on this entire schematic, you will not see a single basic gate that's got bubbles on the input. So what this guy right here is probably right. It's this guy right here that's wrong. So if they would have drawn this as a negative NAND, now that would have made sense. Let's see what I'm talking about. So now I've got to figure out how this whole circuit works. I got to figure out what's going on way over here to figure out how this circuit works. Now this is a kicker right here. So anytime I see these are called, so another thing I want you to look at. So when we do our schematics or do our diagrams, we call our inputs A, B, C, D, E, F. In the real world, these inputs are going to have names. For one thing, I've only got so many letters of the alphabet to work with, right? That makes sense? And then another thing, I would like to have a pretty good indication of what that signal does inside the digital schematic. So this guy right here says it's going to change the direction of something, right? You understand? This says this is going to step. This is going to select something. So the signals are given names basically depending on what they do. So in real schematics, we don't call them A, B, C, D, E, F because that would get very confusing, right? If they can give the signal for a name, then it's easier for me to trace that symbol through. Because we can't give this guy here the name A and then give this guy here the name A, because that would be very confusing. And we've only got 26 letters in the alphabet, right? You understand? And then you got every output would have to have a different one. Every input would have to have a different one. So I would run out of letters of the alphabet real fast. So what they do is they actually give these signals names. But I come over here and I look right here, and if they put a bar over the top, it means it's low. It's true when it's low. So this RD stat, this means this is a low active signal. But look at here, guys, it's connected to a high active output. So we got a signal that says it's true when it's low, and then I've got a gate that says it's true when it's high. So that's a big problem, right? So what I'm trying to do is I'm all the way over here trying to trace this all the way back through this to figure out what's required over here to get that low way over here. Right? You understand? But if this guy right here was drawn as a negative NAND, right? You understand? Now it makes sense. And then that over here, this would be drawn as a negative NAND. This would be drawn as a negative NAND. This guy here is all right. This guy up here would have been drawn as a negative NAND. Now everything makes sense, right? Because the gates are telling you what they're looking for. I'm not trying to figure out what's required on the input to get what? To get this signal all the way over here to go low. because the gates are telling me what they're looking for. And that's a big kicker right there. I got a low active signal, and that's what the bar above it means, right? Being fed by what? A high active output. So now I've got to go all the way back to this thing, all the way back to where? All the way back over to here to figure out what's required over here to get that low way over there. So this guy right here would be hard to troubleshoot because this is drawn in all positive logic. The other one would be a lot easier to troubleshoot because it's drawn in active logic, where the gates change symbols depending on what they're looking for, right? You understand? So this guy, we hated this guy. And we used to troubleshoot this guy to the component level. So we had, they were all, I wish I had some of the boards over here. So every IC was in a socket. And then it came with a little riser. And what you could do is you could swap out the riser and put problems that appeared to be in the chip, which was pretty neat. And then the students would come in and troubleshoot it to the chip level. We don't get in that detail anymore. These are Heath numbers, by the way, the 443, but 74 LS245. Anybody know what that is? It's a bidirectional buffer. So I just wanted to show y'all this and get y'all into those symbols. So you need to start doing what? Learning them. So what we're going to do is we're going to give out a worksheet. We're going to go lab where we do Wednesday, where you're going to give me the title of the gate, but you got to understand a negative and an or are the same gate, right? You understand that? So our 5 basic gates actually have 10. So we have 10 symbols for our 5 basic gates. All right, guys, y'all go lab. I'll give y'all the worksheet. Yeah, put that back in the box for me. Thank you.